deduction of Kepler's second law. Deduction of Kepler's second law of planetary motion. Kepler's second law of planetary motion. So this is the elliptical orbit of a planet around Sun. And Sun exists at one of its foci of this elliptical orbit according to Kepler's first law. And this is the planet of mass small m. And we can denote the distance of the planet from Sun. And this is the planet of mass small m. And the planet revolves around Sun with orbital velocity v0, and v0 is the orbital velocity along the tangent. So we can denote the gravitational pull or gravitational force of attraction on the planet due to Sun. So, and that supplies necessary centripetal force Fc. Here Fc is the centripetal force and Fg is the gravitational pull or gravitational force of attraction on planet due to Sun. This gravitational pull or force Fg acts radially inwards towards Sun, and we can denote the mean distance of planet from Sun. So this is the mean distance. This is the mean distance. This is the mean distance. So r is the mean distance of planet from Sun, and mean distance vector r acts radially outwards. That means from Sun to planet, towards planet, and gravitational pull Fg acts towards Sun. Vector Fg acts radially inwards, and angular momentum of planet, that is vector L, is the angular momentum of the planet, which acts vertically upwards with respect to the horizontal elliptical orbit, provided planet revolves in anti-clockwise direction. A planet of mass m, small m, revolves around Sun of mass capital M, revolves around Sun of mass capital M in an elliptical orbit. In an elliptical orbit, this is the elliptical orbit. In an elliptical orbit, under the influence of the gravitational pull experienced by the planet, the gravitational pull of Sun on the planet, the gravitational pull of Sun on the planet, that is Fg, is the gravitational pull or gravitational force of attraction. And this gravitational force of attraction experienced by the planet, or the gravitational pull or the force of attraction, gravitational force of attraction Fg experienced by the planet due to Sun, supplies the necessary centripetal force Fc, the necessary centripetal force Fc, which acts radially inwards, due to revolution of, which is required for the revolution of planet around Sun. The torque acting on the planet due to the gravitational force of attraction or gravitational force of attraction Fg on the planet, experienced by the planet due to Sun or on the planet, is vector tau equal vector r cross vector fg. Vector vector tau equal vector r cross vector fg. So magnitude of vector tau equal r fg sine phi, not cos phi. It should be sine phi. So here written cos phi, but it is wrong. So we have to make a correction. That should be r fg sine phi, where phi equal 180 degree, which is the angle between mean distance vector of vector r of planet from the sun, and the line of action of the gravitational pull Fg, and the line of action of gravitational pull Fg, vector Fg. In diagram, vector r acts radially outwards and gravitational pull vector Fg acts radially inwards. They are opposite to each other. That's why phi equal 180 degree. Therefore, vector tau equal r fg sine 180 degree. So it should be sine phi, not cos phi, because we have the cross product between r and phi, that is sine phi, and here we can write r fg sine 180 degree. That was incorrect. Now correction is made. So tau equal 0 because sine 180 degree is 0. Tau equals 0 because sine 180 degree is 0. And which is equation? Again, torque is numerically equal to rate of change of angular momentum. So tau equal dl by dt, where L is the angular momentum of the planet which acts vertically upwards, where L is the angular momentum of the planet revolving around sun, of the planet revolving around sun. And the planet revolves anticlockwise around sun with orbital velocity v0 and angular momentum vector L acts. This is angular momentum vector L, which acts vertically upwards provided the planet revolves anticlockwise in horizontal elliptical orbit. Therefore, dl by dt is equal to 0 if we compare equation 1 and 2. So L equal constant means angular momentum of revolution of the planet is constant. L is constant. So again, angular momentum L is twice of mass of areal velocity. L equal to m dA by dt, where m is the mass of the planet and dA is the area. dA is the area swept by the distance vector r of the planet from the sun, in time interval dt. L equal to m dA by dt, and here we can draw the diagram. So this is the mean distance, and we have the planet, and O is the center of this circular orbit or elliptical orbit. And the planet moves from the point A to B in time dt. Planet moves from A to B. This is the mean distance of planet from sun, vector r. And vector r starts to move from the point A at instant t equal t, and it reaches to the point B at instant t equal t plus dt, and dA is the area which the distance sweeps in time. Therefore, 2m dA by dt equal constant. Therefore, dA by dt equal constant, because mass can, in this case we can assume that dA by dt is constant because 2m dA by dt was constant. Hence, the areal velocity, that is dA by dt, areal velocity, that is dA by dt of the planet Areal velocity of the planet around Sun is constant. Is constant. This proves Kepler's second law of planetary motion. Second law of planetary motion.